Our questions for homework last night were on page 652, and we want to take a look at three of those questions. Four of those questions. 2, 6, 7, and 10. Starting with number 2, which is not a problem type question, but just rather a qualitative question. Number 2 says, explain why in a Michelson type experiment, the rotating mirrors have to turn at a very precise frequency in order for light to reach a stationary observer. Anybody have an answer for that question? Yeah, right? Yeah, if the frequency is wrong, if the frequency is not just a very precise value, then the light will never reach the observer and nothing works if the light doesn't reach the observer, right? But why won't it reach the observer? Like why does the mirror have to rotate at a very specific rate for the light to strike that observer? Go ahead, Riley. Yeah, you guys learned yesterday about the law of reflection, right? The angle of incidence equals the angle of reflection. If that light comes back from that mirror on Mount San Antonio or whatever mountain you're doing your experiment on and reflects off of the rotating mirror at the wrong angle, and then it's going to go somewhere else, right? It's going to go somewhere, but it's not going to go to the observer. And if we don't have the light, or the mirror reflecting it, rotating, get my words mixed up here, rotating at the right frequency, then it's going to not strike that mirror at the right angle to be observed by the observer. So you got to have it at a very precise frequency so that the angle of the mirror that's rotating is at the right angle for the light to reflect off of that and get observed by the observer. Okay, if you're too low, you can't see it. If you're too high, you can't see it. Got it? Okay, the next one we wanted to go over was question number 6, I believe. 7? 7 and 8, I guess it was, wasn't it? 7 said, a 16-sided set of rotating mirrors is used to measure the time that it takes for light to travel a certain distance. At what frequency does the mirror need to rotate such that it makes 1/16th of a rotation? I'm going to circle that because we're used to 1/8 of a rotation, right? And the time that it takes the light to travel 3.5 kilometers and back again. I'm going to circle that as well because we're used to like 35 kilometers back there and then back again. You know what though? We do the same thing as we always do. We always start off the same way. What is that way? What do? What do you write down first? Always. The equations. What are my equations? Good, Stefan. V is equal to D over T. T is equal to 1 over F. What does little t stand for in this question? Yeah, it's the time for 1/16th of a rotation, right? Usually it's the time for 1/8, but in this case, it's the time for 1/16th. This would be the time for one complete rotation. Let's sub in some numbers and see what we can find. We're looking for the frequency, so that means we need a speed. We're going to have to assume the speed of light that's given to us on our data sheet. The distance is 7,000 meters, right? 3.5 kilometers there and back again. It's going to allow us to solve for little t. That's the time for 1/16th of a rotation. 7,000 divided by 3 times 10 to the 8. What do we get there? (2.333 times 10 to the minus 5). Remember what we said yesterday and the day before with this? The one you solve for, the time you get, is never the one you want, Sadie. So what do we got to do to get the one we want, to get big T here? Good. If you're going from a little number to a big number, like a little t to a big T, you got to multiply, right? Little t is smaller than big T. A little number is smaller than a big number. A little person is smaller than a big person. Okay? And if you want to go from something little to something big, you got to multiply. So we're going from little t to big T, we're going to multiply. In this case, it's multiplied by 16, though, as opposed to by 8, right? So take this, multiply by 16, we end up getting 3.7333 times 10 to the minus 4. Which we're going to plug into here and solve for the frequency. So the frequency goes up, the 3.33 goes down. Let's just take the inverse of that. We end up getting 2678 or we'd say 2.7 times 10 to the 3 hertz. Usually we get a frequency that's in that range of about 600 hertz. Why are we so far off this time? Yeah, it's so close, and we're using a 64-sided mirror as well, right? If you're using an 8-sided mirror and a distance that's similar to the 35 kilometers that Michelson used, then we're going to get that 5, 6, 700 hertz. Okay, but a question like this, as soon as I see 1/16th of rotation, all bets are off, and then the 3.5 kilometers just adds to that. Yeah.
For this, if it's asking for the frequency of 1/6,
Yeah. Okay, I see what you mean. That's a good question, actually. Understand what frequency is. Frequency is defined as the number of revolutions per second, the number of rotations, I should say, per second. You're looking for the frequency that the mirror needs to rotate such that it makes 1/16th of rotation in that amount of time. We're not saying at what frequency is, what's the frequency of 1/16th? We're saying what's the frequency of the rotating mirror? How many rotations does it make per second if it's going to make 1/16th of a rotation in that amount of time? That makes sense? Number 8 says an 8-sided set of rotating mirrors rotates at 545 hertz. How far away should the fixed mirror be so that we measure the speed of light? This is different than any we've done so far. But we start off the same way. V equals d over t, and t is equal to 1 over f. T would be 1/8 of a rotation. Big T would be the time for one complete rotation. We're going to have to go with the speed of light that's given to us on our data sheet. D is what we're looking for, right? We don't know what T 1/8 is. So we go to the other equation. Big T is, we don't know, but we can find it by saying 1 over 545. Gives us 0.00183. That's the time for one complete rotation. Now, it's not what we want because it's never the one we want, right? So let's get the other one. We have the time for one complete rotation. Let's divide that by 8 to get the time for 1/8 of rotation. Little t is 2.294 times 10 to the minus 4. Let's sub that in here. Look at that. Even though I'm solving for something different than I usually solve for, and then in little d, it's still pretty easy. Solve for a different variable, 3 times 10 to the 8 times that. Gives me 68,807. Is that right? Is that my answer? Oh, it's so close, but man, would it be so easy to mess up on this? That's not my answer. What do I got to do, Matt? You got to divide it by 2. What have I just calculated there? I calculated the distance there and back. What do I want? Just there. So let's divide this by 2. This is one you got to think about a little bit, right? I said to you guys a couple of days ago, oh, the good news is you don't really have to think about these questions because they're all the same. Well, every once in a while there's a little trick like that. You do have to be careful, but it is still very recipe based. This gives me 3.44 times 10 to the 4 meters. You be really careful on that. If that's a question on a diploma exam, then you got to figure 6.88 times 10 to the 4 would be one of your options. You know that, right? Good there? And finally, question number 10, which is, again, pretty similar because it's just another Michelson experiment. V equals d over t. T is equal to 1 over f. Little t is the time for 1/8 of a rotation. And this is the time for one complete rotation. We want to find speed. My distance is 35,000 meters. 17.5 kilometers there and back. The frequency is 1,000 here. So t is going to be equal to 1.0 times 10 to the minus 3. Let's divide that by 8 to get the time for 1/8 of rotation. 1.25 times 10 to the minus 4. And when you solve for speed there, we get 2.8 times 10 to the 8. Hey, I got a quick question for you, sig figs. I said 3 digits for my answer. Shouldn't it be 1 digit because it's an 8-sided mirror? We said one day. We rarely have to worry about this, but we said one day here. I don't know, month or two ago. Sorry? No, no. If you're counting, like a counting doesn't count for significant figures. Let's say there's 20 people in this room. All right, well, there's no chance there's 20.3 people in this room or 20.001 people in this room. If there's either 19 or there's 20 people in this room. When you're counting, it's considered to be an exact number. So you don't count significant figures for that. 20, there's 20.000000000 people in this room. Okay, 20 to an infinite number of significant figures. An 8-sided mirror, there's no way it's 8.01. It's 8. It's exactly 8. So we consider that to be an exact number, and it wouldn't count for significant figures because it's a counting number as opposed to a measurement. You count sig figs for measurements, you don't count them for counting. You know what though? Nice thing about physics 30, like you don't have to be as good at significant figures in physics 30 as you do in physics 20. Okay, in physics 30, they always tell you on a test or an exam, round it to this many digits, right? We still want to know it, but in the end, pay attention to what it says, how many digits to round it to, and you'll probably be okay. Yep. Yeah, go ahead.